First, let me thank the organizers for making this long program happen, and especially for making this second workshop happen. It's great to be here on the UCLA campus. It's my first time here. It's wonderful, and so thanks for the chance of giving a talk here. I talk about some aspects of transporting quantum mechanics by quantum channels. These are typically metric, geometric aspects, so isometries of quantum state spaces, metric properties of Wasserstein distances, and so on. So first I will give a very brief recap of the classical story that everyone knows very well, just to fix some notation, and then I will turn to that concept of mass transportation in quantum mechanics that we are working on. It was pioneered by Dániel Trevisan and Giacomo de Palma. So that kind of transport by channels. And then I will turn to some of our recent results concerning the geometry of quantum Wasserstein spaces with respect to these distances. So the first part will be about metric properties of these divergences. The second part will be about isometries. Okay, this slide is dedicated to Monge and Kantorovich. So I took advantage of making a slideshow and not a chalk talk. And so the problem, as you very well know, is to transport some goods from producers to consumers. And the distribution of consumers and producers classically are represented by Borel probability measures on some underlying space where the transport takes place. And there are different concepts of transport plans. So the first that was introduced by Monge, who was on the left side of the previous page. So his concept was that a plan is exactly a map which pushes forward the initial measure to the target measure. That was proposed in the 18th century. It has some weaknesses. For example, one producer cannot serve two customers in this setting. The relaxation by Kantorovich resolved this problem among others, and it also, so his approach was to model transport plans by couplings. So by probabilities on the product space, such that the first margin is the distribution of producers and the second margin is the distribution of consumers. And then this approach is also beneficial from the computational viewpoint because it's a linear optimization problem on a convex domain. And the cost is just a two-variable function. Little c of xy tells you how much it costs to transport 1 unit of goods from x to y. And so the total cost of the transport is the expectation of this cost function in the state which is described by the coupling. And so it's a linear optimization problem no matter what the details of the cost function are. And how we choose the cost function. So it happens quite often that long transports are proportionally cheaper than short ones. So it makes a lot of sense to choose subadditive concave cost functions, such as the order of the distance, the p power of the distance, where the exponent is between 0 and 1. That's a popular choice. But also, this workshop is dedicated to dynamics, so I should mention that from a dynamical viewpoint, the cost, which is the square of the distance, is of high importance because the kinetic energy is proportional to the square of the velocity. And so if one considers the dynamics of the transport, so a flow of measures rho t, which connects the initial measure and the final measure, such a way that the evolution is governed by a velocity field Vt in the sense of the continuity equation, and one considers this action, which is the average kinetic energy, then the minimizer of this action is exactly the displacement interpolation, and the minimal cost is exactly the the static quadratic Wasserstein distance squared. So that's p-Wasserstein spaces consist of measures with finite moment of order p, and the distance is what you know very well. That's computed by the optimal transport cost when the distance is the p-power of when the cost is the p-power of the distance. One remark about the probabilistic interpretation. So we can recast this problem as finding the minimal expectation of c of xy when x is a random variable with low mu. Mu is the initial measure and y is a random variable with low nu. That's the final measure. And then if you are on the Euclidean space in the quadratic cost case, then finding the optimal transport plane is exactly finding the maximally covariant, those versions of x and y which has the maximal covariance. Those x and y which has maximal covariance. So let me just give a very far from complete list of approaches to non-commutative versions of transport theory, starting from free probability, which was pioneered by Bian and Voiculescu, and one of the dynamical approaches developed by Ammas and Eric Carlen, which relies on a quantum version of gradient flow in interpretation of evolution equations. And the one based on quantum couplings, pioneered by François Gauss and his co-authors. And as I mentioned, we will work mainly on transported quantum channels developed by Dario Trevisan and Giacomo de Palma. And I should mention also the work of Zhitkovsky and his colleagues, which may be summarized as a semi-classical approach. And there are some others that, of course, should have been mentioned here. So, and what we have done is a non-quadratic. So the definition of non-quadratic problems in the setting of transport by quantum channels, and to introduce that definition and the Wasserstein distances that were induced by that kind of transport problem, I would like to go through a simple example instead of doing everything in the largest generality. So classically, if we have one particle moving freely on RD, then the state is a Borel probability on the phase space, right? So on RD times RD. And then what's the interpretation of the squared quadratic Wasserstein distance of two states of this classical physical system? In this case, it's the minimal expectation of a sum of squares, or the square between the vectors consisting of the momentum and position of the first particle and momentum of position of the second particle. And this is the picture that will prove useful when one defines these quantum optimal transport problems and induced distances. In that setting, in the quantum setting, the states are not Borel probabilities, but okay, maybe wave functions or mixed states are represented by trace class operators, which are positive end of unit trace. And the measurable quantities, instead of measurable functions on the phase space, they are self-adjoint operators, typically or possibly unbounded. And what is the key is the measurements rule, Bohn's rule, is that if we measure the quantity described by A, then we should consider its spectral resolution, denoted by E of A. And then the probability of measuring a value that belongs to the interval AB when the system is in the state rho is exactly the expectation of the spectral measure of the interval AB in the state rho. So one quantum state describes a bunch of classical probability distribution depending on which observable we are interested in. So So let us fix some a finite number of observables that we are interested in. In the previous example, it was just momentum and position. And let those random variables, so xk and yk, denote the measurement results. So xk denotes the result of measuring ak in the initial state, and yk the same thing in the final state. And the probabilities are given by Born's rule. Okay. How we should how quantum channels realize transport? What is the correspondence between couplings and channels? First, so this is completely the work of Palma and Trevisan, so nothing new here. But let me first show the analogy with the classical case. So what's the classical correspondence between Markov kernels and couplings? So the correspondence is that if we sort of multiply the kernel by the initial measure, we get a coupling. So in more details, that if you put the initial measure in the diagonal of a matrix and you multiply with that the kernel from the left, then you get exactly a coupling. Coupling of two consecutive steps of the Markov process, which is generated by the kernel. So that's one component that should be mimicked in the quantum case, and the second is that, as far as I can tell, is the Choi-Miałkowski isomorphism, which is a representation of a channel on a Hilbert space H by a state on H tensor H star, which is the following: that one takes a maximally entangled state and let the channel phi act on the first component, or in other words, let phi tensor identity act on this state. And then what you get, that completely encodes the map phi, the channel phi. And their idea was that instead of letting this phi tensor identity act on one of the maximal entangled states, they just let it act on the canonical purification of rho, which is the following. So one takes the square root of rho by spectral calculus, and then so why H tensor H star? Because the trace class operators are canonically isomorphic in a linear way to this space and not to H tensor H. So that's why the H star appears. So by that canonical isomorphism, one gets an element of H tensor H star, which is here. That's a vector corresponding to square root of rho, and the rank 1 projection corresponding to it is the canonical purification. So let this phi tensor identity act on this canonical purification, and that will give rise to a coupling. So the moral is similar to the classical one, that we should multiply sort of the Markov map, so the quantum channel with the initial distribution. That's the rule of thumb. And one can check the marginals. So the first marginal will be the image of the initial state under the channel phi, and the second marginal is a transpose, transpose in the abstract sense of the initial state. And the other way around, once you are given a coupling, you can explicitly construct the channel at least on the support of the initial state. Yeah.
So, a stupid question. What is the Fj and the Ej?
Yeah, so Ej, that's just some orthogonal basis, and Fj, that's a dual basis in H star.
Oh, dual.
Sorry, I didn't say that.
Thank you.
Thanks for clarifying this. Okay, so these are the marginals that can be computed easily. So that gives rise to the definition of couplings. So coupling should be a density on H tensor H star, such that the first marginal is the final state and the second marginal is the transpose of the initial state. And yeah, so there's nothing new here beyond this first line. Just some explanation of things that you know very well. And so as I started to propose, we obtain these random variables by measuring our observable quantities on different copies of a system, which is in the state P. So it's a state of it's a composite system. The state is described by P, which is a coupling of rho and omega. And we take capital K independent copies of this system being in the state P. And these copies are independent. So once we obtain the law of xk and yk, then we get the joint law by simply taking the product. So again, by Born's rule, if we take the spectral projection corresponding to the event that we measure yk, so that the outcome of measuring ak on the second system is exactly yk, and the same story here, so that the spectral projection corresponding to measuring xk on the first system, this gives rise to a genuine probability measure on R2k, because we have 2k real measured values, and then we are almost done, because what we're interested in is the cost. Is the cost of this genuine real probability measure on R2k, and that's simply the integral of the classical cost function little c against this this joint law. But it's much more convenient to introduce a cost operator such that this whole cost will be of the form of an expectation of a cost operator in some state. So that's what we are doing here. That we define a cost operator which corresponds to the so this calligraphic A, that's the collection of observables A1, A2, and so on, AK, and this little c, that's the 2k variable classical cost function, and then by this 2k variable spectral calculus, we define an operator. We simply integrate this little c against a spectral measure, which we obtain by the spectral resolution of the observables that we are interested in. So again, and this is just the last time that I will tell that this spectral projection, this corresponds to the event of measuring x1, y1, x2, y2, and so on, xk, yk. And so the transport problem should be to minimize the expectation of this cost operator in a state which is the tensor power of order k of this coupling p.
Excuse me, would you mind recalling us what are the input variables to your problem? So you're starting with densities and then you have some xk's, or that is?
Yeah, so the inputs are the densities rho and omega.
And then we
and also the observables A1 and so on, AK. These are the parameters, and these they have their own spectral resolution.
Okay, so they are also given.
Yes, that's a parameter of the problem, and therefore they are also parameter of the cost operator. Right, that's one parameter, and the other parameter is the classical 2k variable function. Thank you. And A good news concerning this problem is that just like in the classical case, optimal plans do exist, and the proof is nothing beyond the proof of the classical case. So there's a nice tightness argument in the original paper of Dániel and Giacomo that the set of quantum couplings is tight in an appropriate sense, and therefore a minimizing sequence has an appropriate limit, which is a minimizer. It's fine. I'd like to mention some special case when the classical cost is the LQ norm to the power p. Because in this case, the cost operator has a very concrete form. So we had this spectral integral by definition, but it's simply that we take these expressions. So AK tensor identity minus identity tensor AK modulus on the power of order Q. And we plug it into the K subsystem. So this little K means that there are tensor products with identity at all components, but at place K. And especially if we take the p power of the LP norm, then this whole cost operator factorizes. So this parenthesis outside vanishes, and then so the cost operator is really just a sum of components which depend only one observable quantity. And then with this definition, so with this observation, we define the p Wasserstein distance as the minimal expectation of this cost. Of course, at the power of order 1 over p if p is bigger than 1, just like classically. And there was a proposition for this the quadratic distance that was defined before by Dániel and Giacomo, and they proposed a modified version because these distances may be non-zero even if the two arguments are the same. So states have positive distance from themselves, which has some good reasons, but it is undesirable for some reasons, for other reasons. And they proposed a modification which they called Wasserstein divergences. And so absolute, with a clear analogy, we may also define Wasserstein divergences of order p like this. So this dAp for the distance, and then this is the divergence. And so we already see that this definition is not, it has some weaknesses. That's described in this preprint from January. But it also has some desirable properties. I guess that this is not the final definition of a good p-Wasserstein divergence for p being different from 2. Okay. And now I'd like to turn to the isometries and metric properties, which which are for the quadratic case. So in that case, this classical cost function little c is simply the Euclidean distance of two vectors in Rk, and then the cost operator factorizes and has this beautiful form. And then the corresponding Wasserstein distance can be given in a nice way, simply in terms of the channel realizing the transport, and not in terms of the coupling. So what one should observe that just like in the classical case, the distance, the squared quadratic distance, is the sum of the two second moments, right? So second moment in the initial state, and second moment in the final state, and there's a cross term which corresponds to sort of covariance, and it's a non-trivial fact that the identity channel always realizes the self-distance, so the distance of a state from itself. And therefore, there's an explicit formula also for the divergence, for the quadratic Wasserstein divergence in terms of the channel. So the only difference is that one should replace the second moments by these guys. So the trace of square root of rho times aj squared. And then in the second times rho should be replaced by omega, and so that has the potential of being a genuine metric, and we did some steps in this direction, and proved. Okay, so it refers to a previous paper. So we proved the triangle inequality in a special case when the state sort of in the middle is pure. Then later, we in the preprint that I cited from this January of 2025, we relaxed to the assumption that at least one of the states should be pure, no matter which one. And we had some nice email exchange with Melchior, who proved this also some quite general under some quite general assumptions, but not in exactly full generality. So in complete generality, it's still open, it's still puzzling. But at least for this case, the proof is so simple that I even want to highlight the steps. Because the thing is that if rho is pure, sort of in the middle, then there's no optimization at all on the left-hand side. So if rho is pure, then the only coupling is a trivial. So the distance, and therefore also the divergence, is given in terms of the product coupling. So it's absolutely computable, and we have these simple formulas for the divergence arising from the product coupling. So these terms that replaces the second moments, and the cross term, the covariance or the cross term that's simply the product of so that's simply the covariance. And the only trick is that okay, on the left hand side there's some optimization here because tau and rho may be mixed, but that helps us because this should be a lower bound for the left hand side. So if we consider the product coupling and we obtain the inequality even for the product coupling, that's fine. Then we are done. And so the only trick we use is that there's a nice Cauchy-Schwarz inequality for the Hilbert-Schmidt inner product. If you have state x and an observable y, then the trace of square root of x times y squared, which appears here and here instead of the second moments, that's bounded from below by the square of the trace of x times y, so the square of the expectation of y in x. And then the right-hand side, so this signed combination of the square distances, we can bound from above in an easy way, which is a Euclidean inner product, right? So it's an inner product on Rn. So we just do another Cauchy-Schwarz in Rn to make an upper estimate, and then we use the same Hilbert-Schmidt Cauchy-Schwarz to obtain a further upper estimate. So this first line is just the Euclidean Cauchy-Schwarz, and the second line is the Hilbert-Schmidt Cauchy-Schwarz, and then we end up at the left-hand side, which is the end of this argument. So it's really simple in this case. And then what we did later is to relax the assumptions to the case when any of the state is pure, that's enough. That's more sophisticated because then there's genuine optimization on the left-hand side as well. And I'd like to say a few words also about the isometries, results. So again, we consider the simplest possible state space, the quantum bit state space. And we considered some distinguished cost operators. So we call a map on the qubit state space Wasserstein isometry if it preserves the Wasserstein distance. That's fine. I emphasize this definition because it becomes non-trivial because the Wasserstein distance is not a metric. So it can happen with this definition that an isometry is non-surjective, that's fine, but even non-injective. So that's a bit counterintuitive. And first we consider a cost which we call the symmetric cost for some reason I'll explain later, which involves as observables exactly the three Pauli operators, Pauli matrices. So we have these three distinguished observable quantities. We can write the cost operator in a very explicit way. And what we find is that the isometric group of the qubit state space is exactly the group of Wigner symmetries, meaning that they are exactly the unitary or anti-unitary conjugations, which is also nice because in the Bloch sphere model that I guess most of you know, when the state space corresponds to the unit ball of R3, and sort of the Pauli matrices point in the direction of the three axes. In that model, unitary conjugations corresponds exactly to orientation preserving orthogonal transformations, and anti-unitary conjugations correspond to orientation reversing orthogonal transformation. So somehow this group of quantum Wasserstein isometries is exactly the classical isometric group O3 in the Bloch ball model. So that's sort of a compact, nice result, and the things get much more complicated if we forget about sigma y. So we discard one of the Pauli operators and consider the cost, which is generated simply by the qubit clock and shift operators, which are sigma z and sigma x, or in this notation sigma 1 and sigma 3. So this is the shift and this is the clock. And again, there's a very simple form of the cost, and there's a more complicated form of the isometric group. And instead of describing all the formulas, I would like to somehow explain the story that now the cost operator chorus involves the sigma x and the sigma z operators. So the x z plane in the Bloch sphere model is distinguished, and somehow the y axis is different. And therefore, there's an O2 component of the isometric group. So no matter what orthogonal transformation you do in the x z plane, that's going to be a Wasserstein isometry. It's fine. And what happens in the y direction? So the interesting thing is that if you consider pure states in the Bloch sphere ball model, they are exactly on the sphere. With the pure state, you do almost whatever you want. So you can send one state to its opposite, in such a way that the opposite state is fixed, right? So that's a non-injective isometry. You do with these pure states almost whatever you want. That's described by this this calligraphic F. Okay, I don't want to define all the notation. So you do whatever you want on the pure states, and there's also a C2, so a reflection symmetry that if you reflect with respect to the XZ plane uniformly, that's again an isometry that corresponds to the element-wise conjugation. And so we don't have a clear understanding of what the isometric group is. We have this lower bound, which is that you do an orthogonal in the XZ plane and the uniform, possibly uniform reflection plus whatever you want to do on the surface. These are clearly isometries, and the upper bound for the isometric group is that you have this orthogonal component in the XZ plane, and you do whatever you want. So you should switch the sign of the Y component everywhere else. And there are some numerics which indicates that in fact the lower bound is going to be the isometric group. So there's some kind of rigidity. The mixed states should be mapped together. They cannot be mapped separately to their negatives. And so the consequence of these first two results is that if we have all the Pauli operators, then there's a simple structure of isometries. If we discard one, then there's a more complicated structure. So we wanted to take it to the extreme and consider the cost which is given only by one operator, say sigma z. And then the group of isometries, sort of isometries, is even more rich. So if one has a map which fixes the modulus of the Bloch vector in the Bloch model, and also it fixes the z component of the Bloch vector, or it uniformly maps it to the negative, then it's going to be Wasserstein isometry, which is somehow counterintuitive, because it means that if so whatever you do on a circle, which is the intersection of a plane describing the third component of the Bloch vector and the sphere which describes the modulus of the Bloch vector, whatever you do on that circle, that's going to be Wasserstein isometry, and you can do it on all circles independently. So there's a very rich structure of isometries in this case. And yeah, so we really want to remove the assumption of one of the states being pure in the case, and we would like to prove triangle inequality for quadratic quantum Wasserstein divergences. That's a future plan. For p-Wasserstein divergences, we really want to find the proper definition, because the current one has some weaknesses. And once we get that, study the metric properties. And also, we are keen to study isometries of state spaces of larger systems, and try to prove or disprove data processing for these modified Wasserstein distances. So these divergences, because it's clear that data processing inequality in general cannot hold for quantum Wasserstein distances. That's clear even by this cost operator generated by sigma x and sigma y, because the whole unitary group is larger than the isometric group. So there are unitaries which are not isometries. This is in contrast with the symmetric case, when all the polarities are involved. In this case, all the unitaries are isometries, and that's a non-trivial fact. which is surprising because typically in this isometry business it is the case that that it's easy to find a lower bound for these isometric groups, say the unitary groups. So it's easy to see in most of the cases that all the unitaries are isometries, and the hard work is to prove that there are no others. And now it's also requires quite some computation to prove that the unitaries are actually isometries, because in other cases it definitely fails. So even the unitary channel can increase the Wasserstein distances, so there's no DPI for Wasserstein distances. What about divergences? Yeah, and I'd like to give the credit to these colleagues that I have been working with on these problems, and I'd like to thank you for your attention.